So let's start by having a look at the nuclear model. So we're looking at nuclear physics, introduction to nuclear physics, and obviously we need to have some type of visual representation of what we are thinking about. So here's the classic model of the atom that you've probably been used to seeing since late primary school years, early high school years. We have our nucleus and we have our electrons orbiting. So we're going to focus on the nucleus here, and we're going to call the particles in the nucleus, we're going to call them nucleons. The nucleon number is the number of protons plus the number of neutrons inside the nucleus. Now we know that the model of the atom has an intrinsic energy about it. We know that the electrons are in motion, so the atom itself, because of these electrons being in motion, we can think about it as an energy system, where if the electron is moving, it has a vector component. At each point in its motion, that vector component gives it kinetic energy. So the electron has kinetic energy, and therefore the atom has kinetic energy. If we, however, delve closer into the nucleus, so we take, let's say, a magnification of the nucleus, and we start to explore things like the forces that exist between protons and neutrons, or protons and neutrons, then we discover a few interesting patterns. Now we know the repulsion exists between protons, but there must be an attraction that exists between protons and neutrons, and possibly neutrons and neutrons. If this did not exist, then no atom in the universe would be stable, and we know, well, that's not true. So when we think about this, we think that there is some type of interaction between the repulsion forces and the attraction forces. Now, the sum of these forces, if we think about the totality of these forces in a stable atom, we say if the attractive forces are greater than the repulsive forces and the nucleus is stable, it's going to maintain its stability. Now we can think about this, the forces involved, in another system, which is the planetary system. Now most of us are aware that the moon revolves around the Earth, and the force that keeps the moon in orbit is called gravity. And we also know that any object above the Earth's gravitational field has potential energy, because that potential energy can be converted into kinetic energy. An object dropped from above the Earth falls towards the Earth with a velocity. So this idea of forces producing some type of potential energy is not new. This same thing we can say occurs within the nucleus. So we can think about this electron as being pulled towards the positive nucleus, but it never actually quite falls into the nucleus because it's got this velocity it's moving with. So that the forces in and the forces out are always balanced along this path. Now that's a good analogy to use. The analogy between the gravitational and the atomic or nuclear. Now, the force by which the moon is held in the Earth's orbit is referred to as a gravitational force. Most of us are aware of that. The potential energy that's given to the electron as it orbits around an atom, this is due to the electrical force And in physics we call this electromagnetism. So electromagnetism is one of the 4 fundamental forces in the universe. So really, this whole topic 1.2a, is going to be about how forces play out within the nucleus and the implications that does have for stable or unstable nuclei or atoms. Alright, so what you will need to be able to do by the end of this particular subtopic is, first of all, you need to be able to describe the nuclear model, keeping in mind that to describe means to state what its parts are and what their role might be. Explain why protons repel each other. So again, when explaining why protons may repel one another, you'll come back to looking at the charges of those protons. Then we look at defining the strong force. Now we'll talk about that, the force we've just introduced, the electromagnetic force, and we'll talk about that force that holds the nucleus together. And then we will look at the stability of the atom or the nucleus and how that pattern evolves across the periodic table. So we'll be using on the screen the abbreviation SNF for strong nuclear force because we'll be using that quite often. So before we can begin to actually quantify things like how much energy is released, what the potential energy of a nucleus might be, we have to have a working understanding of how to use the fundamental particles. Now, just to give you an idea, we know that the nucleus is made up of the protons and neutrons, and you can see here that a proton's mass, and that's the thing we're going to focus on here. We're not going to have a look at the force at this time, which has to do with the attraction or repulsion forces. Yes, we're going to talk about that in the context of the force being there because protons actually repel each other, but we'll look at that idea of the electromagnetic force further down the track. But let's focus now on the masses. Now, just as a comparison, you can see I'll focus on these two. So here is the mass of an electron in kilograms, and here is the mass of a proton. You can see there's a significant difference. Now, if I was to do a comparison, so if I was to find the ratio of these two values, what you'd find is that the mass of a proton is about 2,000 times the mass of an electron. So what that tells us is that when we are actually calculating the mass of a nucleus, even if we leave the electrons out, the difference is not that significant. Now we need to be able to convert between masses that are given in kilograms because, you know, we don't want to work with numbers this small. So therefore we're going to use the atomic mass unit U, and you can see it over here that you've got the atomic mass of a proton is about the same as a neutron, which is about the same as a hydrogen. Now there are small differences there which we will talk about later, but at the moment one atomic mass unit simply about 1.67 by 10 to the minus 27 kilograms. So if we want to convert from atomic mass units to kilograms, we use the factor conversion method. So these are the conversion factors we can use. So if we want to convert to U's, we multiply by this fraction, or if we want to convert from U's to kilogram, we multiply by this fraction. Now, the other thing I want to draw your attention to is this hydrogen atom down here. Now you can see that the hydrogen atom is really close to the mass of a proton, and we know that if we were to include the electron mass in the hydrogen atom, then we would have to include the electron. So the mass of an electron from the table in kilograms plus the mass of the proton, and if we calculate that out to 2 decimal places, you can see really we don't need to focus on it too much. So in nuclear physics, because we're going to be using the changes in mass to signify how much energy is lost or given off, or energy required, we're going to ignore the mass of the electron. Now when we're working with nuclei or nuclide, in other words, we're looking at the element of a particular atom and its nucleus, we use this convention where A represents the number of protons and neutrons, or the nucleon number, and Z represents the proton number. Now, if we were to consider the magnitude of the force, so I just want to talk a little bit around the actual forces that exist in here, because as this nucleus gets larger, the repulsive forces become larger, so therefore the attraction forces that are required to hold the nucleus together and keep it stable need to become greater. So let's just quickly review the 4 fundamental forces. So we've already mentioned these. We've got the gravitational force, and we've got the electromagnetic force, which is the force that derives the repulsions in the nucleus. But then we must have another force that's stronger than the electromagnetic force. Physicists call this the strong nuclear force. Now that strong nuclear force is responsible for the energy, the vast amounts of energy, or the large amounts of energy that are released, or the potential energy that is released from the nucleus. Now there is a 4th fundamental force. It has to do with the particles themselves. So what is a proton made up of? It's made up of some smaller particles that are held together by another force referred to as the weak nuclear force, that plays out in the release of things like beta particles, but we'll talk more about that later on. So if we want to understand the strength of the strong nuclear force and its range, we can use this relationship here, which has been developed. So this equation has been developed empirically. In other words, experiments have verified it, and what it shows us is that the radius of a nucleus, now the radius is dependent upon the nucleon number. So as the nucleon number increases, as the number of protons and neutrons increase, of course, so does the radius. But what this tells us is that the force, the strong nuclear force, has got a limited range, and that range is very small. When the nucleus radius becomes greater than this, the atom or the nucleus starts to become unstable. So this represents roughly the range within the strong force acts to keep all these nucleons together and to keep the atom stable. So let's have a look at the features of the strong nuclear force. So there are 4 things that we can identify from these conclusions. Now first of all, the strong nuclear force is independent of electric charge. Now what that means is that the force acting between a proton and a neutron, or a proton and a proton, or a neutron and a neutron are the same. Secondly, The range of action of the strong nuclear force, as we've sort of mentioned already, is very small, and we use that figure, which was around 10 to the minus 15 meters. Thirdly, this range plays a very important role in the stability of the nucleus. So as the nucleon number increases, the volume of the sphere representing the nucleus increases, and therefore its radius increases, causing the strong nuclear force to be weaker, and it has less ability to hold everything together as it would otherwise. And fourthly, when we think about the repulsion forces, we can't assume that this one proton just repels this one. The fact is that this one proton affects or repels every other proton in the nucleus. What you see here is a graph that represents the number of neutrons in any nucleus plotted against the number of protons. In other words, the neutron number n against the atomic number z. Now, ideally, what we would find is that the number of protons and neutrons would be equal, and as you can see, they are equal. So if we follow this line along, they are equal until we get to about there. So we're looking here at a proton number of 25 and a neutron number of 25, so equal numbers of protons and neutrons. So we can explain this, we analyze it, and we can explain it in terms of our understanding of the strong nuclear force. So up to about 25, z equals 25, we say the proton number is equal to the neutron number. So the radius of the nuclei in these atoms are below this strong nuclear force range. Our radius is about less than 10 to the 15 meters. As we begin to increase the number of protons, so here we're at 40, you can see the number of neutrons required now all of a sudden increases to 50. Now from this we can say that beyond 20, so that's anywhere from 20 all along through 40, more protons are required to increase a strong nuclear force so that the nucleus remains fairly stable. Now obviously there's a limit to this. As we increase the radius number, so when we get to about here, you can see that according to our schematic here, this represents our stable nuclei. Beyond this point here, which is z equals 83, there are no more stable nuclei. In fact, they start to become very unstable. So we can conclude that all nuclei beyond n equals 83, and by the way, that represents the atom bismuth, are unstable and therefore quite radioactive because they tend to lose nucleons, so they cannot be held anymore within the nucleus. So just to complete the picture here, we have some nucleons that may be within an atom whose proton number is greater than 83, and the circle shows the range of the force. So any of the nucleons that sit outside this range are vulnerable to repulsion forces, and therefore what will happen, these have the potential to be ejected from the nucleus. So they fall outside this range, and as a consequence we say that the electromagnetic repulsions can actually cause the nucleons to be ejected. Now this actually happens in the form of things like alpha particles. We'll talk more about these when we look at radioactive decay. But in conclusion, by losing this matter, or by losing this mass, the nucleon mass, that tends to decrease the radius of the nucleus and eventually bringing it back to within the strong nuclear force range, and hence it improves the stability of the nucleus. While this discussion is fresh in your memory, it might be a good idea to come back to the learning goals. How well can you describe the nuclear model, explain why protons repel each other, define the strong nuclear force, and how well can you explain stability in terms of the strong nuclear force over short distances? Sit down and try and write some responses or answers, treating these like questions. It would be a good way to test yourself to determine if you can do this or not.